mechanism of action, we shall have our nitrogen mustard like this. And the R group. This chlorine is highly electron withdrawing. It is an electron withdrawing group, meaning that it will pull the electrons towards itself. This carbon will be partially positive. So this nitrogen, having its lone pairs, will attack this carbon. When it attacks this carbon, this chlorine, the chloride will go. So we shall have this. And the R group. But now the nitrogen is positive. So this is the aziridine cation. This is the aziridine cation, and it's highly electrophilic. It is electrophilic. We say that they have highly electrophilic structures which are highly reactive, meaning that this nitrogen is unstable. It will try to pull the electrons back, meaning that this carbon, this one and this one, they can be partially positive also when it takes the electrons back. As it pulls electrons toward itself, we shall have the partially positive cation here as a carbon. So when you find the nucleophile, but most will say it's the guanine, the N7 of the guanine. Guanine is like this. This is the guanine structure. This is the guanine structure. Now, this guanine is this N is the N7 of the guanine. This is the position 1. This is 1. This is 2. This is position 3. This is 4. This one will be 5, 6, and 7. So this N is highly nucleophilic. It is the one which will come to attack this carbon. So I've represented it as a nucleophile just, but it is the N7. When this one takes the electrons, the nucleophile will attack the carbon, the carbocation. Therefore, we shall have this. We shall have the nucleophile, which is the guanine. And this arm remains with its chloride, and the R group is untouched. But remember, this guanine, it's on the DNA strand. It's on the DNA strand. It's on the DNA strand. Then it's the same mechanism which will happen to this arm also. This one will take the electrons toward itself, leaving this carbon unstable. This one will attack the carbocation, meaning that the chloride will go away. Then we have the N with R. Here we have the nucleophile, which is the N7 on the guanine on the DNA. Here we shall form the aziridine cation again. We shall have nucleophile again coming to attack this carbon because the N is unstable. It has the negative inductive, it has the negative inductive effect. So when it takes the electrons, the nucleophile will come and attack the carbocation. Then we have this. it's on the DNA. Even this side, it's on the, we have the nucleophile on the DNA. So this DNA will try to move away from the covalent bond. As it is liberated from the covalent bond of the nitrogen mustard, we shall have, okay, remember this N is having 3 bonds. So here we shall have the nucleophile attached to the nitrogen mustard, so it will be plus. Even this one will be plus, this N will be plus. And we have the chloride. This chloride, which has gone, it's present. It's like that. So when we are liberating the DNA from the covalent bond, when it is liberated from the covalent bond, we shall have this. Shall leave the guanine alone. And that we shall have two DNA. By this DNA or these two DNA, they are damaged. They are damaged because they have lost the guanine. So they are unable to replicate. So this is the DNA damage. If it happens in the cancer cell, meaning that the drug is working because it's a chemotherapy. If it happens to the cancer cell, but if it happens to the normal cell, we shall have the side effects, of course. Yes, for the chemistry of our structure. And you have also the R group here. The pharmacophore is the base beta haloalkylamine. This is the alpha carbon. You see, this is alpha. This is the beta carbon. Alpha carbon, beta carbon. It is this because you have two. At the beta carbon, we have the halogen. This chlorine and this chlorine. The two chloride atoms. They are at beta carbon, so it is base beta haloalkylamine. This is the alkyl group, and this is the amine group. So this is the pharmacophore. So this one determines the pharmacodynamic. So it determines the pharmacodynamics. The R group changes, and for it determines the pharmacokinetics. As we saw that this chlorine is highly electron withdrawing. It is electron withdrawing group, which has the negative inductive effect, meaning that it will pull the electrons towards itself, making that this nitrogen, instead of attacking the proton in the solution or in the medium, instead of attacking the proton in the medium, it will attack the carbon here, meaning that it reduces the basicity of the N. So this one reduces the basicity. Of the nitrogen atom. Instead of attacking the proton, it will attack the carbon. So the pKa of these nitrogen mustards will reduce, meaning that at the normal pH, which is 7.4, at a pH of 7.4, most of this drug will stay unionized because we're expecting this. Okay, let me put here R group. Expecting this N to attack a proton in case it encounters the proton. But because of the electron withdrawing group, it will attack mostly the carbon, this carbon, which will be the carbocation, as we have seen the mechanism of action. So this one reduces the basis of the N, meaning that most of this drug at that pH will be unionized at 7.4. This enables the formation of the azidine cation. The one we have seen. So enabling the action of the drug such that when formed the azidine cation, you can have the nucleophilic attack, internucleophilic attack. The inter. This nucleophilic attack is from different compounds. These chlorines, they are very essential because of the electron withdrawing effect. When it pulls the electrons, mean that it reduces the availability of these electrons to attack the proton in case it encounters the proton in the media. Enables the formation of the azidine cation. When we form the azidine cation, we can have the internucleophilic attack. Hence, the drug allocated the N7 of the guanine, which is the target for the nitrogen mustards. Then, this Arab group can be aliphatic and can be aromatic. Aliphatic, for example, we have seen the microrethamine where we have the CH3. This group is electron donating group, meaning that it will push the electrons towards the nitrogen, meaning that it increases the basicity or the nucleophilicity of the N, meaning that this drug having the aliphatic group will be highly reactive. It will be highly reactive. For example, the microrethamine. Increasing the reactivity to reduces the oral use of this drug or the oral administration. To reduces the oral administration of that drug, because it will find the water present in the GIT. It can inactivate that drug. We are going to see the mechanism, aqueous instability, meaning it's highly reactive. For the aromatic, this one, we have the aromatic group, which reduces the nucleophilicity of the N. It stabilizes it by resonance. When you have the resonance, it reduces the reactivity. When it reduces the reactivity, this one provides the oral use of the drug. So we shall have the oral use of these drugs, which have the aromatic group at this position. Because they are less reactive, this one, due to increased reactivity, we shall have a lot of the side effects. At the moment the azidine cation is formed, we shall have the nucleophilic attack. So it will reduce the specificity of the drug. We shall not have the cell specificity. We shall not have the cell specificity because of the high reactivity. So there is no time for a drug to go to the cancer cells, but this one can give time for the drug to reach the cancer cells because it is less reactive. So there is decreased side effects for this drug. So the R group determines the pharmacokinetics. Here we have the oral bioavailability. the tissue penetration, and also the excretion of the drug, excretion rate, also the metabolism of the drug. All these ones are determined by the R group. Let's go to the aqueous instability and we see how these drugs are affected by the aqueous environment. Yes, about the aqueous instability of these drugs are affected by the aqueous environment. For example, we have this. The solutions or the buffering solution. The buffering solution is made to be acidic, such that if there is an acid, we shall have the protonation. For example, this drug will exist as an ion, like this. This reduces the formation of the azidine cation because there is no lone pairs of electrons to attack this carbon. So this reduces the reactivity of the drug. So the buffering solution is made acidic such that we have the protonation. This reduces the formation of the azidine cation. That's it. So how does the aqueous environment affect the drug? We shall have this. This is the drug. As it forms the azidine cation, this chloride will go. We shall have this. As this one pulls the electrons toward itself to stabilize, the water will come and attack the carbocation there. So we shall have this with OH. So it's the same mechanism which will happen to this mustard arm also. We shall have this. This is the dehalogenated diol. This is what we shall have. Here we shall have loss of 2 hydrogen chlorides. 1 H from here and this chloride. We shall form this. This is one of the mechanisms. This is the mechanism A. But you can have the water coming directly. For those highly reactive nitrogen mustards having the R here, which is when it is the alkyl. When it is alkyl group or aliphatic. When it is aliphatic. They are highly reactive. We can have this. Remember, this chlorine has the negative inductive effect. It pulls electrons towards itself. So water can come directly like this. This oxygen attacks the carbocation directly. Then the chloride goes. We shall have loss of 2 hydrogen chlorides. Then we form the dehalogenated diol with the R group. So these are the 2 different pathways which we can have in aqueous instability. We can have the formation of azidine cation, or we can form the diol directly. Let's talk about the specific drug.